Okay, so we'll make an attack now on one of these models. We're going to get the MNIST data set again, which is going to be, I think, these digits where you're trying to recognize the digits. Let me just clean off this old stuff. Okay. Now we're going to get the SecML library, the machine learning security library, because it has the ability to craft efficient attacks. So, all right. So we're going to have 100 training set samples, 500 validation, and 500 test set samples. And this is going to show these 784 pixel images again. Um, and here's what they look like. There. So there's images, and we're only using 5s and 9s, and the goal is to tell the 5s from the 9s. And here they come with labels, so you know what the right answer is. So we train a classifier to learn to tell the 5s from the 9s. And it gets up to 93.6% accuracy at doing that. Now we're going to make an evasion attack. And what this does, you could try randomly changing images to fool the model, or you could try to change the image in a way that would fool a human. But what this is going to do is it looks at the model, it knows all the weights in the model, it's going to analyze the model to find out which pixels it cares about the most, and it's going to modify those pixels to fool the model as much as possible. It's going to find the weak spots and carefully plan how to give it images that will confuse the model. That's what this SecML Advanced Attacks module does. So the attack has started. It's now predicting what are the most effective changes to make in an image to most confuse the model. And now the accuracy, it made a reduced set to practice on. The accuracy was 100%, but after the attack, the accuracy goes down to 12%. So the attack is very effective. And now I think what is most instructive is to look at what it did. Here's what it did to those images. These are the original images, and all it did was add a little bit of snow, and now it thinks it's a 5. It added these little bits of dot. Now it thinks it's a 9. Now it thinks this one is a 5. And it thinks this one is a 5. This wouldn't fool a human at all. And that's, what I've been saying. The model is doing some weird thing to choose some pixels to decide whether it's a 5 or a 9 that is not what a human does. So these little ghostly pixels down here make it wrong. It's now 100% wrong at identifying all these images. And there's variety. You can try different varieties here. So that shows the problem. And there was China has a lot of automated taxi cabs. And a research group a few months ago published a paper where they found they could make a little bumper sticker looking thing with a few dots on it. And when you put that on a car, the taxi cabs can't recognize it as a car at all anymore. Because just like this, a few pixels will confuse it. And so now the automated taxi cabs will hit those things because they can't see them anymore. So that's a useful thing to know. And I should mention there's a defense against this, which is what you might imagine. This is called deep neural rejection. And this one took me quite a while to work out. But the deep neural rejection involves you add another bit of machine learning model to your model, which measures just some parameter about the shape of the images, and then you figure out which images look funny. Their shape is significantly different than an average one. And if you add the deep neural rejection model to your model, what happens is when you poison these images, just like we just did, by adding these little snowy dots that make it miscategorize them, this model with the deep neural rejection is able to figure out that those images look funny, and it refuses to categorize them. It now puts a -1 here. It can tell this doesn't look like a normal image. Those little dots make it in the 1% outlier of an unusual looking image, and it will now recognize the poisoned images and refuse to classify them. So the most of the poisoned images are now rejected now that you give it that option. So that is a defense to notice if these images just don't look right anymore. So that's one defense that works. So that's what I wanted to show you.